So now to our second learning target. We want to be able to solve quadratic equations that are in the form x squared equals a number a. And this is rather simple. To solve a quadratic equation that's in that form, x squared equals a, since x is being squared in the equation and we want to know what x is, not x squared, we solve that equation, x squared equals a, by basically just square rooting both sides of the equal sign. So if I want to solve for x, I have to get rid of that squaring. I would do that by square rooting, remembering that a positive number has two square roots. So we end up with x is equal to the positive square root of a, or x is equal to the negative square root of a. So if all you have is an x squared, you don't have an x with it, you can simply solve that equation by merely square rooting both sides of the equal sign. And so that's what property 6.1 tells us, that if you have any real number a, and you have x squared is equal to that real number a, that will be true only if x is equal to either the square root of a or x is equal to the negative square root of a. Let's demonstrate with this next example. Let's say we have the equation x squared equals 45. Well, once again, we want to solve for x, so we have to undo that squaring. So we're going to need to take the square root of both sides. But always remember, every positive number has two square roots, one that's negative and one that's positive. So when you square root something that's squared, you get just x. So when you square root x squared, I should say, you get just x. The square root of 45, well, we're going to want to simplify that. So we've got to think about our list of perfect squares, 2 squared, 3 squared, 4 squared, and so on. The largest of those that divides evenly into 45 is 9. So I can think of the square root of 45 as the square root of 9 times the square root of 5, because 9 times 5 is 45. Well, the square root of 9, of course, is 3. So our solutions here end up being positive and negative 3 square root of 5. Okay, so hopefully so far you're not finding what we are covering here in lesson 6.2 to be too complicated. There is one last part, and this is our last learning target that I mentioned, and that's to do with solving problems that involve right triangles, but also those right triangles that also include a 30 and 60 degree angle. So work with radicals, and in that property that we just learned, that if x squared equals a, then that's only going to be true if x is equal to the square root of a or the negative square root of a. We're going to use that property along with what we know about radicals, including the Pythagorean theorem, when we're dealing with problems that have right triangles in them. Now, just a reminder, the Pythagorean theorem tells us that the square of the legs of a right triangle added together are equal to the square of the hypotenuse of the right triangle. A hypotenuse, you recall from your days in geometry, is the longest side of a right triangle. So this would be C. Your legs would be A and B. And A and B could be interchanged, but C has to be the hypotenuse. So we're going to be using that Pythagorean theorem here to solve some problems that involve quadratic equations. And you can clearly see that this is a quadratic equation, a squared plus b squared equals c squared, because the highest exponent on any variable is 2. So let's say that a 50-foot rope hangs from the top of a flagpole. When pulled taut to its full length, the rope reaches a point on the ground that is 18 feet from the base of the pole. Find the height of the pole to the nearest tenth of a foot. So here's a picture that shows what is described there. You can see it's 18 feet when it's pulled taut, from the base of the rope to the base of the flagpole, and that you can see that the rope itself is 50 feet long, and you can clearly see that that is the hypotenuse. So we want to use the Pythagorean theorem to solve for P. So our Pythagorean theorem again is a squared plus b squared equals c squared. Now c has to be the hypotenuse, and in this case that is the length of the rope. So c squared would be 50 squared. A and b are going to be the two legs of the right triangle. So I'll make A the P, and I'll make B the 18. Those could be interchanged, but again, the hypotenuse has to be C. So now I just have to do a little simplifying. 18 squared, with the help of my calculator, is 324, and 50 squared is 2,500. Again, I'm trying to solve for P, so I have to undo the addition by subtracting 324 from both sides. And that'll leave me with P squared is equal to 2,176. Now I'm in a situation where I've got x squared equals a, so I know to square root both sides. In this case, though, there's only one reasonable square root, and that's the one that is positive, because you can't have a side of a right triangle have a negative length. So when I square root 2,176 and round my answer to the nearest tenth, I find that that pole must be 46.6 feet in length.